Hey guys, it's Adam the Science Tutor. Welcome back. So today we're going to be doing part 2 of the cyclohexane chairs and the stability. So new concept, there's wedges and dashes. So wedges and dashes are a way in organic chemistry to tell what's facing or where it's at on the molecule. So wedges are facing towards you, so it's a wedge, it's pointing at you, and then a dash is pointing back or away from you. And in a cyclohexane chair, wedges are always facing up and dashes are always facing down. So that's a key thing to remember. I'll write these things down, but remember that wedges, what it means is that it's pointing at you. So it's pointing at you, dashes are pointing away from you. So dashes are back, wedges are in front. So I'm going to add this molecule here, cyclohexane, with a methyl group and a ethyl group. So two different substituents. Now I'm going to have you guys convert it into a chair. And we're going to see which chair is more stable. So we have to our drawing of it. So here's our chair. So that's our cyclohexane. Now let's add the methyl. Let's say this is our 1 carbon. Let's say this is our 2 carbon. Remember that the placement is important. But here you can pick anywhere to start. So I'll put this one as my 1 carbon. This is a 2. So that means everything else has hydrogens attached. Of course, because it's like over there, it has hydrogens attached everywhere else. But we'll do this just for practice. Okay, so this is our 1 and 2. So this one's down. Okay, so we have this one's up and it has down. This one's down and it's up. Okay, so like I had said before, dashes prefer going down. So this is our 1 carbon. Which one's going down? Axial is going up. So this is going to be the hydrogen because these are in retroframe. So this means that the hydrogen, unless specified, is like this. So it's wedged out. So that's our hydrogen, it's facing up, and then our methyl groups, the equatorial, which is more stable, over here, right here, is our ethyl group. So that's in a wedge, and wedges want to face where? Wedges want to face up. So our axial is facing down, our equatorial is facing up. So we're going to put our ethyl group right here, and a hydrogen right here. So is that the most stable? We won't know. So I'm going to go ahead and erase this, and we're going to do our chair flip, which we discussed in our video from last time. And if you guys want to check that out, click the link. I don't know where it's at on the YouTube page, but click the link wherever it comes, and you guys can see it. But okay, so we're going to do the chair flip. So chair flip. Okay. So the chair flip, we're going to do opposite side. Opposite side. The importance of this is to keep things relative. So this was our 1 carbon, this is our 2 carbon. So that means our 2 carbon would be right here, and that means our 1 carbon would be right here because it's flipping. So we need to keep that still relative. So this is our 1 carbon, 2 carbon. So after flipping it, this is our 1 carbon, 2 carbon. Okay, so hydrogens are all attached all the way around. We don't need to add those. It's not necessary. It's just like in everything else. The hydrogens are just, it's implied. So on our 2 carbon, we have an equatorial, an axial. On our 2 carbon, our 1 carbon, we have an equatorial and axial going down. So like I had said, what's up stays up, what's down stays down, courtesy of Dr. Davis. Once again, check out the last video if you want that. So on our 1 carbon, it's right here, the hydrogen is facing up, so this would be our hydrogen. What's facing down is our methyl group. Therefore, and then on our number 2 carbon, our ethyl group is pointing upward. So it's going to be on the axial. So it'll be a CH2 ethyl group, and then this will be our hydrogen. So which of the two is more stable? Well, as we know, equatorial is more stable. So we want our bigger substituents on equatorials. We don't want them on axials. Axials, they'll run into each other, they'll bump into something. So this one, our first one that we drew, is the more stable because the ethyl group and the methyl group are on equatorials. So we have to slightly not even debate. This one is more stable because they're more, it's on the bigger substituents, and the substituents are, all these substituents are on the equatorials. So I'm gonna go ahead and give you guys another problem, but it's fairly simple if you guys write it out and just look at it and remember this easy step. So equatorial is more stable, axial is not. So let's go ahead and I'll give a new problems from the start. We're going to draw our cyclohexane. I'm going to use the same groups, but I'm going to put them in different areas. So it was wedged. I'll put a propyl group, and it's wedged. And hopefully you guys wrote down the notes for this last one, or you guys can check out the worksheet below, and that way you guys know what a wedge and what a dash is. You guys need to know that. This is the importance of this video. And then our dash will be our methyl group. So it's almost similar, but we'll see the difference. So let's draw our first chair. So I'm gonna go up, so it goes down. If you want to learn how to draw this, go down to the our last video. So, okay, so let's say this is our 1 carbon, 2 carbon, 3, 4, 5, 6. As you know, it doesn't exactly matter. So, as long as you keep them relative. So let's say this one is our, 1 carbon, 2 carbon, 3, 4, 5, 6. Okay, so you have to keep it relative to our chair flip. So our 1 carbon doesn't have anything. This will be our 2 carbon. 2 carbon, it has, it's an axial, equatorial, then 3, and we also have it on the 4 carbon. So you have axial, equatorial. And remember, since they're both facing down, that's where the axial goes, and then the equatorial one is mirror of the opposite side, so it's mirrored. So that's how you draw the things. Once again, it's on the on the last video. Check it out. So let's see. So we're gonna go with the 2 carbon first and check it out. So we have the CH3, we have the methyl group on a dash, so we know it's back, it's away from us. It's pointing away from us, so it's pointing down. So our methyl group will be on the axial because it's going down. The equatorial is facing upward. It's going north. It's going or northish. It's going up. And then on our 4 carbon, everything else has hydrogens. On our 4 carbons, this propyl group, and it's a wedge. So wedges like to go upward. So it's going to be on the equatorial. So C. Okay, and then our hydrogens here, and our hydrogens here. So we have, so you could write it down on the side too. We have 1 methyl on a axial, which is not comfortable for the molecule because it's it's obviously bigger than a hydrogen. We want a single hydrogen, and you want your heavier substituent on the equatorial because it's more stable. We have 1 methyl there, and we have a propyl substituent on the equatorial, which is good. We want that. It's a check mark because we want that. Now over here, I'm gonna go ahead and erase this, and we're gonna draw the chair flip and discuss which one is more stable and why. So for this one, we're gonna go. Okay, so once again, it's important to keep the relative positions correct. So this is our 1, so this one will be our 1 carbon. Drop some right now. This one would be a 1 carbon. This one would be the 6. That means this one's a 2. This one's a 3, 4, 5, 6. So you can keep them relatively positioned well. So this one's a 1, 2. Our 2 carbons, one that has the methyl group, and our 4 carbon, 1, 2, 3, 4. Our 4 carbon up here is the one with the propyl group. So everything else has hydrogens. We know that. I'll add those if you guys want to see them. So this one has an axial group going up, and it has an equatorial going down. The 4 has an equatorial going down and an axial going up. So we're going to see this. Okay, so oh, I didn't add it. Okay, my bad here. But this one was a dash, and this one was a wedge. Okay, and you can also add the wedge or dash in this chair molecule. That's probably a better habit than just leaving it how I was doing it, because you forget. It's easier to see, just so you know. So right here, where you're having our methyl group is on our 2 carbon, and it's facing down. Whatever is facing down has to be facing down. So it's now on a axial or on an equatorial position. So CH3 right here, methyl group right there, and then hydrogen up top. So that's the other substituent. And then our propyl group's a wedge, so we know it's wanting to face upward. So our propyl group will be here, and our hydrogen will be there. Okay, so which one is more stable of the 2? And let's go ahead and write it out. So we have 1 methyl on the axial over here, and a propyl on the equatorial over there. Over here we have an equatorial methyl, and then we have a axial propyl. So tell me, what's the point of this and why are we doing it? So we want our biggest substituents, here we're gonna write it here in text, but we have our bigger substituents on the equatorial, because it's more room for them. It's more room here than it is here. So we have more room equatorially. We have a lot more room. So you need to remember or watch out for that, and you need to know that we want the bigger molecules on equatorial. So what's a bigger molecule, a methyl or a propyl group? So if you guys remember from way back, my first video, we have my acronym is monkeys enjoy perfect bananas. So N for methyl, E for ethyl, P for propyl, B for butyl. So we obviously know that our methyl only has 1 carbon, our propyl has 3 carbons. So the propyl group is bigger, therefore we want the propyl group equatorially, which is this one. So this would be the chair conformation you would draw, not this one. So if they were asking for the most stable conformation, you would draw this one right here. So I'm gonna go ahead and give you guys another problem you can work on, and we will do it real quick. And then I want to also say another way to memorize where each of these go is that equatorial equator runs this way around the Earth, world history, global history, Earth. So it goes around like this. So it's an equator, equatorial goes sideways, and then axial runs north-south. So let me give you guys another problem, and we'll work on it. So here's a cyclohexane, and we're going to put methyl group, and remember this does not have preference, so you want to put it on the most stable, as long as you want to put it on the more stable, which is equatorial. And we're going to put a wedge with it. And then we're going to put a dash. So we have a propyl group on a wedge, an ethyl group on a a dash and a regular methyl. We're going to go ahead and number this. I'll put 1, 2, 3, 4, 5, 6. So it's on the 1 carbon, 2 carbon, 3, 4, 5. Okay, so let's go ahead and put our first cyclohexane chair up, and let's see how it looks. So we're going to go this way, so this is down, so we're facing up. Okay, so let's put this as our 1 carbon. 1, 2, 3, 4, 5, 6. It's a little ugly, but it's rushed. And some professors will care, so be careful about the way you draw it. Drawing it kind of. So what do we know about wedges? Wedges are going up, and that's 1, 2, 3. That's a propyl group, so this is up. Let's go ahead and put our equatorial axial anyway. So up, down, we have down, up, we have up, down, down, up, we have up, down, and we have down, up. Oop. Shoot. Equatorial. Okay, so let's add, we know most of these are covered with hydrogens anyway, but we're going to go ahead and start. So we know that wedges want to be up, they're facing up, so this is a propyl. We're going to put pro, so that's just a little slang for propyl group. So that's propyl, and we have a hydrogen here. We have hydrogens here. This is our 1, this is our 2 carbon. So our 2 carbon has ethyl, so we're going to put, and that's dash, so we know it's facing down, so we put ethyl, and we put a hydrogen. On our 3 carbon, we know we have 2 hydrogen groups, so hydrogen, hydrogen. On our 4th carbon, we have both hydrogen groups too, hydrogen, hydrogen. Alright, that's our 5th carbon. Up here we have that methyl group, and we're going to put this on the equatorial. So we have a methyl group here and hydrogen. So what do we see here? What do we recognize? We automatically recognize that the propyl group and the ethyl group are on the axial. So automatically, what can we suggest, or what do we know? Well, we know that this is not going to be the most stable. So no matter what this is, or no matter what the opposite one is, or the chair flip is, we're going to know that that is the correct answer, because then we know flipped. Well, let's just check out and see. So we know flipped that it will be so once again, pardon me, I'm rushed, I'm drawing quickly, but so we know this is our 1 carbon. So our 1 carbon is now flipped. It's right here. We have one going up, one down. So we have that's facing up, right? The propyl group is facing up. So now the equatorial is facing up. So we have a propyl and the hydrogen. And then this is our 1 carbon, our 2 carbon. So our 2 carbon, flip that, is up here now. We have the ethyl going downwards, which is also an equatorial, which is a good check mark for us. Hydrogen, that's an ethyl. And then, let's see, flip, this is flipped this way. So this is our 5th carbon, and it had no preference, but we put it there on the first one, so you have to stay consistent. That's important, stay consistent. So it's downward, so it's facing down. So that's down, up. So we do have a methyl group here and a hydrogen here. So obviously we do not want the methyl group on the axial position, but since that's the way we drew it first, we just stayed consistent. And since it has no preference because it was just a line, then we could change it almost, but this would be the more stable anyway. And it's the right answer on the test day. Because the ethyl and the propyl groups, which are the biggest substituents, are in equatorial position, so they have enough room. Look how big a propyl group. A propyl group has 3 carbons and hydrogens all attached. It's long. It's a big group. So we want them. we want them on the on the equatorial position to spread out and to not bump into other things. We do not want another big substituent here to bump into the methyl group. Just the same. We do not want two big groups colliding into each other, because that would just make the molecule unstable, and that's not what we want. So remember, equatorial for world, axial goes across the world, equatorial, the equator, and axial runs top to bottom. Wedges and dashes. Wedge is pointing where? Wedge is pointing towards you. Dashes are pushing back away from you and away from the molecule. Dashes are back, dashes are down, wedges are up, wedges are facing towards you. I hope you guys watched the last video so that you guys can get a better idea. I know I touched base on a little bit more things there. This was part 2 where just adding wedges and dashes and the complexities. So if there is a time where there's just a methyl group and a ethyl group, you're gonna have to pick them, and if they're on the 1-2 and you have to pick which one will be on the equatorial. You want the bigger substituent to be on the equatorial position. So that goes with any other subgroups too, like alcohols, halogens, anything else, bromides, anything. You want the bigger molecule to be on the equatorial position because it has more space and it's more stable for the molecule. So come test day, think stability, think of what can I do to make the chair the most stable. Thank you guys for watching. Please subscribe. It's Adam the Science Tutor, and yeah.